So lecture 6.3, Beyond Proportional Design. So using proportional design like we did in the preceding lecture, 6.2, the closed loop poles are restricted to the root locus, right? All we can do is increase the gain, decrease the gain, move those closed loop poles along the root locus, and that's all we can do. Often the root locus does not pass through the closed loop pole location specified by performance requirements, okay? Which is a bummer. Therefore, design techniques can be that can move the poles to desired locations are indicated. So that's what we're going to do. We're going to learn how to move that root locus around and just manipulate it in general. So we consider two classes of controller: proportional integral derivative, or PID, and proportional lead lag. And in fact, we're really only going to talk about PID controllers, other than this really high-level discussion of lead lag. If you take Control 1 in the fall, we'll talk more about lead lag controllers too. PID controllers are ideal integrators and differentiators, and therefore require active circuits for instantiation. So you have to have external power like op-amps and whatnot in your circuits. Proportional lead lag controllers can be considered approximations of PID controllers, and these can be realized in passive circuits, so with capacitors, inductors, resistors, etc. So that's the main difference there. We will build controllers incrementally by cascade compensation, which is illustrated in figure 6.2. So here's the figure. Here's our usual control block diagram with feedback. The command error gets fed to the controller. Here's our plant. And there's our output that we're trying to control. So the controller has a this cascade topology to it. So we've got the gain. So what we do is we first design a gain controller using the same method from lecture 6.2, and that's our first controller design. Okay, it's the first start. It's the easy one. It's the one we know how to do already. Just gain control. Okay, adjust the gain based on the root locus. Get as close as we can, and then the next step is to do some compensation. So say we did the gain, which is our P control. Then we might do an integral compensator, which we'll learn about today. So that would be C1, this block, this compensator, which would be the integral, or the I control. And then we might add another compensator in, say the derivative compensator, and that would be our D compensator, our derivative control. So we would then have a PID controller. So the controller is comprised of the proportional gain and the compensators that you include as well. When I say add on, what I mean is include as well. I'm not talking about mathematically adding. We're actually mathematically concatenating in a multiplication in the Laplace domain. Okay. So that's our control scheme. That's how we'll design controllers. We're going to do it incrementally, doing an initial gain control, and then we're going to do compensation using other techniques. So we'll learn each technique, each compensator technique separately. And what we'll do is we already learned P. Today we'll learn I. Wednesday we'll learn D, and you can put them together, PID, by just including this last bit of design at the end of the integral controller. So I can just show them to you in increments, and then you'll be able to do PI and D. So you can do the whole thing, PID. And I'll show you a PID controller on some hardware on Wednesday. So I'm excited about that. It'll be V fun. Can't stop saying V everything now. It's just so cool. I just feel like a cool kid for a minute. Okay, so this means that we're going to do P control, and then say if we need it, integral compensation, and then if we need it, derivative compensation. Okay, and those compensators will allow us to do a couple things. The integral, as we'll see in a moment, will allow us to give ourselves a better steady state error situation, and the derivative will allow us to have to move that root locus around as we desire. Okay, get some better transient response characteristics usually. Sometimes it'll also be there for just stability as well. If a root locus doesn't go to the left half plane, then you can use a derivative compensator to move it there. So, but integral is focused on steady state error. Derivatives focus on transient or stability. Okay? All right.